Welcome to the video lecture on proving trigonometric identities. Trigonometric identities allow us to rewrite trigonometric functions in terms of other trig functions, and as a result allow us to simplify expressions and make it easier to solve many trig equations. For example, if we wanted to solve this following equation for x, sine x times cotangent of x equals to a half, it would simplify the equation considerably if we note that because cotangent of x is cosine over sine, then when we do sine of x times cosine over sine, those signs are going to cancel out, giving us just cosine of x equaling a half. And we know where cosine x equals to a half. It equals to a half if x is pi over 3 in quadrant 1 or 5 pi over 3 in quadrant 4. So those would be the values of x where the equation is true. Another example would be, suppose we wanted to simplify the expression 1 plus sine x times the quantity secant x minus tan x. Well, one thing you could notice is that secant of x could be rewritten as 1 over cosine x, and tangent of x could be rewritten as sine x over cosine of x. Those have a common denominator, so we can consolidate them into a single fraction and make it 1 minus sine x all over cosine x. And then if you do top times top over bottom times bottom and FOIL across the top, the middle terms will cancel out, and you'll just get 1 minus sine squared x on the top all over cosine x on the bottom. 1 minus sine squared x is part of that Pythagorean theorem, or Pythagorean identity, which says sine squared plus cosine squared always equals to 1. So if I solve that for cosine squared, then that tells me that cosine squared is the same thing as 1 minus sine squared. So here we're just doing a little bit of substitution, and then cosine squared over cosine x, one of those cosines cancels out, and we just get cosine x. So what that means is that this whole big expression is really just cosine x. And wouldn't it be simpler to just work with cosine x than all of this big product? Sure. So that's why we're going to be talking about how to use identities to simplify expressions and figure out how to turn them into simpler things to work with. In this section, we learn how to develop additional identities from the fundamental identities. Some of these additional identities are also worth memorizing because they are used so frequently. Recall that an identity is an equation that is true for all values of the variable for which the equation is defined, which means it's always true no matter what your input x happens to be. An equation that is only true some of the time for some values of the variables is called a conditional equation. So let's see some differences here. X squared minus 4 is a difference of squares which could be factored into x minus 2 and x plus 2. So these two statements on the left and the right side of the equation are equivalent. They're equal to each other, so that makes this an identity. As opposed to over here, x squared minus 4 isn't always going to equal 3 times x. It will sometimes, but not always. You can show that if you were to let x equal to 1 in this first equation, it's not true. So 1 squared minus 4 would give you negative 3, and 3 times 1 would equal to positive 3. So this is what we call a counterexample, a value of x that shows that this is obviously not an identity because there are values of x out there which make it not true. This one over here on the left is that Pythagorean identity that we just talked about. Sine squared x plus cosine squared x equals to 1, and that is always true, so it is an identity. Similarly, tangent of x, defined to be sine x over cosine of x, that was also one of our earlier identities that we knew to always be true by definition. So all three of these are identities. Over here, sine of x does not always equal to cosine of x. If you were to let x equal to 0, sine of 0 is 0, but cosine of 0 is 1. So this, again, is an example of a counterexample for x that shows that this is not an identity because there are values of x which make it not true. So therefore, it is called a conditional equation. There are values of x that do make it true, like pi over 4, but there are also values of x that make it not true. And then finally, tangent of x equals to cotangent of x. If, again, we let x be pi over 4, these would be equal. but if we let x be pi over 3, then they're not equal. Okay? So it's easy to show that an equation is not an identity. All you have to do is find one value of the variable for which the equation is not true, like these three numbers right here. Okay? However, it is much more difficult to prove that an equation is an identity because you need to show that the equation is true for all values of the variable. And obviously we can't substitute in every possible value out there, so we need to figure out an alternative procedure for showing that something is an identity. Now before we jump into our steps, let's talk about some of the basic trigonometric identities, and these are things that you would be expected to have memorized and know them very well because you will need them in this section of notes. This is a very tough topic sometimes for students, proving trig identities, and one of the major reasons why is because there's a lot of basic trig identities like these listed here that you're assumed to know and be able to use well. So if you don't know these very well, it's just going to make proving other trig identities much more difficult. So we have our quotient identities here for tangent and cotangent. We have our reciprocal identities for cosecant, secant, and cotangent. We have our Pythagorean identities. Sine squared plus cosine squared equals 1, tan squared plus 1 equals secant squared, and 1 plus cotangent squared equals cosecant squared. Sometimes you will need variations of these. In other words, if you take this first Pythagorean identity, sometimes we're going to be solving it for sine squared and substituting in 1 minus cosine squared instead. Or similarly, cosine squared could be substituted in with 1 minus sine squared. Sometimes this second one here, we'll solve it for tangent and write tangent squared equals secant squared minus 1. And for this third one, if you solve it for cotangent squared, that's equal to cosecant squared minus 1. Occasionally, you'll need to remember those even-odd identities. Remember that cosine and secant are even, and the other four are odd. So sine and its reciprocal, cosecant, and tangent and cotangent are also odd. So that means if you had a negative inside of your parentheses, you could pull that negative out like this if you're odd. If you're even, that negative just gets absolved and just disappears. Okay? So here's our procedures when we're trying to prove trig identities. One of the hard parts about trig identities is there's not always going to be one way to do the problem, and there's multiple strategies that you want to consider. So here are just some suggested things to look for. Number one, select one side of the equation and start there. Usually what you're going to do is pick the harder side, the more complicated side, and try to transform it into the other side of the equation. So you always want to work with one side only, turning it into the other side of the equation. Step 2, you're going to be using lots of algebra and all of those identities we just talked about on the last page to help transform one side of the equation to the other side. Some things that are sometimes helpful to do, and I'll show you examples of what to look for, would be things like finding common denominators, factoring, eliminating complex fractions, and writing sums or differences of quotients as single quotients will sometimes help with transformation. Another thing that's often helpful as well is writing all of the functions in terms of sines and cosines. Sometimes you'll want to try that if everything else doesn't seem to be working for you. And third, always keep your goal in mind. As you manipulate the expression on one side of the equation, you always want to keep in mind what it is you're trying to turn it into, and that will help you decide what steps to take. Note, and this is very important, it is not acceptable to do something to both sides of the equation simultaneously in an attempt to prove an identity, because doing something to both sides may result in changing an expression that is not an identity into one that is. For example, sine of x we know doesn't always equal negative sine of x. That is not an identity. However, some students might try to square both sides to show that we have an identity here. So sine squared x equals sine squared x. When you square both sides, that negative disappears. So sine squared x does equal sine squared x. That is an identity. But it wasn't when we started with the original equation, sine x not equal to negative sine x. So in other words, don't do things to both sides of the equation simultaneously, because that may affect your identity and turn it into something that is or is not an identity. So let's do a bunch of examples here. All right, let's start with one that's relatively straightforward. We want to prove that this equation is an identity. Cosecant theta times tangent of theta is equal to secant of theta. So here's one strategy that you're going to want to work with. Look at your two sides of your equation. I always tend to start with the side that looks a little bit more complicated, because that gives you more possible things to work with. So in this equation, I like that left side. To me, it has more difficulty in it. It has more stuff that I can convert. So what I want to do is somehow take this left side, I'm just going to recopy it, and I'm going to turn it into something else with the goal in mind of turning it into a secant. So what could I do here to help transform this into a secant? Well, we know that there's a relationship with cosecants and tangents and sines and cosines. So maybe let's convert everything here that we see in terms of sines and cosines. So cosecant of theta, what is that the same as in terms of sines or cosines? Based on that reciprocal identity, cosecant is the reciprocal of sine. So I'm going to substitute that in. Tangent of theta is defined to be sine of theta over cosine of theta. That's that quotient identity. Now if I convert these, what I'll notice then is when I go to multiply these two fractions together, I have a sine theta on top and bottom. So those cancel each other out, leaving me with a 1 over cosine theta. And that, by the reciprocal identity, turns into secant, which is exactly what we were trying to prove, so we got it. Notice that I didn't do anything to that right side. I only worked with the left side and worked to transform it into the right side. Okay, next example. If you look at these two sides, obviously there's more stuff on that left side other than just this 1. So I'm going to be working on the left side and trying to show that it's equal to just a 1. So what am I going to want to do here? Lots of choices. You certainly could change these to sines and cosines if you want. But what I notice here is that there's a little bit of algebra that I could do first. This is just a product of two binomials. And so if I wanted to just go ahead and FOIL this out, what would we end up with? Let's just go ahead and multiply. We'd get cosecant theta times cosecant theta, which is cosecant squared theta. We'd get a positive and a negative cosecant theta, cotangent theta from the inner and the outer terms. So those end up canceling each other out. And then on the end, I'm going to get a positive times a negative, so it'll stay negative. Cotan times cotan is cotangent squared. So that's what I have so far just from foiling, just from doing a little bit of algebra. And when you see these cosecant squareds and cotangent squareds, what should be popping into your head are some of those Pythagorean identities. And as I mentioned before, the better that you know them, the easier it's going to make doing these trig identities. Because if you don't have them memorized, you're never going to figure out what to do from here without having to scramble through your book and try to look some things up. So it's better to have it memorized now so you won't have to waste so much time figuring out what to do next. So the Pythagorean identity that I'm going to use here is that one that says 1 plus cotan squared is equal to cosecant squared. Now I have x's in my identity, but it would work for thetas as well. So what I'm going to do is I'm going to go ahead and substitute in for this cosecant squared theta this whole sum 1 plus cotangent squared theta. So this becomes that. And I'm subtracting cotangent squared theta from that sum. These two things cancel out, giving me 1, which is what I wanted, so I got it. Okay? All right, let's try another one here. 9 secant squared x minus 5 tangent squared x equals 5 plus 4 secant squared x. All right, you do not want to be moving things across sides here. What we're trying to do here is transform one side into the other. So don't be tempted to try and add or subtract terms or solve this. You're not trying to solve this equation. You're just trying to prove that it's always true. And the way to do that is to start on one side of the equation and turn it into the other side. Now, both of these sides have a bunch of stuff involved. I tend to say that the left side here is a little bit more complicated because it has two different trig functions. So that's the side that I'm going to work with. So I'm going to start with this left side. And what should be popping into my head right now is when I see tan squareds and secant squareds is that Pythagorean identity which says that tangent squared of x plus 1 equals secant squared of x. Now notice our goal here. This is an opportunity where you want to keep your goal in mind. This is my left side, and I'm trying to turn it into this right side. Notice that the right side only has secants in it. It doesn't have any tangents. So I kind of want to get rid of this tangent and turn it into a secant if I can. So that means I don't want to substitute in tan squared plus 1 right here because that's putting tangents into the problem that I don't want. Instead, I want to change this tangent squared into something in terms of secant. So what I'm going to do is manipulate this Pythagorean identity, and I'm going to solve it for tangent squared by subtracting that 1 to the other side, and then I'm going to substitute in for this tan squared this secant squared x minus 1. And that way, what I have on this left side only has secants in it and no tangents anymore. Now I do have this minus 5 in front of those parentheses, so let's go ahead and distribute. And then 9 minus 5 gives me 4 secant squared x plus 5, and by the commutative property of addition, we can just switch the order around, and now we have exactly what we were trying to get, so we've proved it. Okay? Now these trig identities, they take a lot of practice. The more experience you have doing them, the easier these are going to become. But the first time you try solving these or proving these, they are going to be tricky because you're just not used to looking for or doing what you need to do to get to that end result. It just takes a lot of practice. So be patient and be prepared to be a little frustrated the first time around. All right, here's my next identity that I want to prove. Again, that left side to me looks a little bit more complicated than the right side, so I'm going to work with that left side. Now on this one, notice that you have two fractions being added together. This is pretty common in these trig identities, so one suggestion that I would recommend here is whenever you have two fractions that you're either adding or subtracting, you want to probably work with a common denominator. Try to get a common denominator, and that will usually help you make some progress towards your goal. So here my common denominator would just be these two denominators multiplied together. So I would have a 1 plus sine alpha times that cosine alpha. Now, since this first fraction already had the 1 plus sine alpha, it's missing the cosine alpha. So that's what I need to multiply by on top and bottom. So cosine alpha times cosine alpha would make this cosine squared alpha. Then we're adding to that this second fraction. It already has the cosine alpha. It's missing the 1 plus sine alpha. So that's what I need to multiply by on the top. So for now, 1 plus sine alpha times 1 plus sine alpha is 1 plus sine alpha quantity squared. In my next step, let's go ahead and FOIL that out and let's see what it is. So I'm going to leave my cosine squared alpha the way it is for now. And when I FOIL out this quantity squared, don't forget your middle term. You're going to get a 1 plus 2 sine alphas in the middle plus a sine squared alpha. Now, what you're on the lookout for are some of those identities. When you see a cosine squared alpha plus a sine squared alpha, you have to know that that's 1. That's that Pythagorean identity. So these two added together become a 1. So we get a 1 plus these other two terms that we had, 1 plus 2 sine alpha, and then obviously 1 plus 1 is 2, so we get 2 plus 2 sine alpha. And factoring is a very common thing to do in these trig identities. Look at that numerator. You can factor out a 2. And that's good news for us because that factor on top in parentheses is exactly the factor that we have on the bottom. So this is going to become 2 over cosine alpha, and that is a secant because the cosine is in the denominator, so it becomes that reciprocal identity. So this is 2 secant alpha, which is exactly what we were trying to prove. So we got it. So when you see fractions, think common denominator. That's almost always a good strategy and a useful one that makes some progress for you. Now this next one, I'm going to warn you right now, this one is a challenging one, and you probably, if you were given this without any kind of hint, you probably would have no idea what to do to solve this. And as I said before, it just takes practice and experience, and having done these problems many, many times before, when I see this, I think that left side looks a lot more involved than the right side, so I'm going to start with that left side. But initially, it doesn't really have anything to work with. I can't use any of my Pythagorean identities because I don't have any squares. I can't convert anything into sines and cosines because it already is. I don't have any fractions, so I can't get any common denominators. So the trick to this one is probably something you would never think of on your own, and you only would think of it once you've done it before in the past, and that is to multiply by something called a conjugate. And we do this a lot in radicals. For example, if you saw 1 over 2 plus square root of 3, to rationalize the denominator, do you guys remember you would multiply this by 2 minus root 3 on top and bottom, and then go from there? Well, that's what we're going to do here. We're going to multiply by a conjugate. So I am going to take this fraction on the left side, and I am going to multiply by a version of it. And again, this would just take some sort of trial and error to kind of figure out what to do. What I'm going to multiply by is the exact same expression that's in the numerator, but I'm going to change this minus in front of the cosine to a plus. That's what kind of a conjugate does. It kind of takes the opposite sign in the middle. Now, how would you know to do the conjugate of that one? You don't. You just have to try something and cross your fingers and hope that it leads you to where you want to go. So it just kind of takes a little bit of practice. And if something you do doesn't seem to be getting you anywhere, then chances are you need to try something else instead. So if I did this and it wasn't leading me or making any progress for me, then I would go back and I would maybe try the conjugate of the denominator or change one of the signs somewhere else. Okay? So again, this is all just sort of instinct and experience coming into play. So I'm multiplying by this expression on the top and the bottom. So really I'm just multiplying by a big fancy version of 1. That's why we're not sort of affecting this identity at all. We're doing something that's valid because we're just multiplying by 1, which doesn't change the original expression. But it's going to convert it into a slightly different form that will be a little bit, hopefully, easier to work with. So let's see what happens. And I'm going to warn you here that this is going to get messy fast because we're taking 3 terms times 3 terms, and you do need to FOIL all of that out. So we're going to do a sine times a sine, which is sine squared, a sine times a positive cosine, and a sine times a 1. Then we're going to take a minus cosine times sine, minus cosine times plus cosine would be a minus cosine squared, and a minus cosine times 1. And then finally 1 times each of these. Alright, now lucky you, we get to do that all over again in the denominator. So now we're going to do sine times sine, sine times cosine, and sine times 1. Then we're going to do positive cosine times sine, positive cosine times positive cosine, and positive cosine times positive 1. And then we're going to do minus times each of these. So all of these 3 become negative. Now you may be saying, okay, this doesn't look like it's getting any better. In fact, it looks like it's getting worse. But our goal here, our hope is that a lot of these terms will cancel out. Plus, we're also getting some signs involved, some squares involved. So hopefully we can use some identities as well. So let's look carefully at the numerator here and see what's going to cancel out. Sine theta cosine theta is the same as cosine theta sine theta, and these are opposite signs, so they will cancel out. My sines are the same sign, but my cosines are opposites, so those are going to cancel out. And so it looks like what we're left with here is a sine squared theta on top. We have a sine plus a sine, so plus 2 sine theta. And then we have a minus cosine squared theta, and we have a plus 1. Now let's look in the denominator. I have a plus and a minus sine, and a plus and a minus cosine. So we're left with sine squared, a sine theta plus, or a sine theta cosine theta plus a cosine theta sine theta. Those are really the same. So we're going to get 2 of those. So 2 sine theta cosine thetas. Plus we have this cosine squared theta, and then we have this minus 1. Okay, now we want to look for some identities that we can use. One identity that I see right away that we've used already is that sine squared plus cosine squared is equal to 1. And that 1 is going to cancel this minus 1 on the bottom. So in my denominator, we're going to be left with just this 2 sine theta cosine theta, and all of these cancel out. So in your denominator, it just got a lot simpler. In the numerator, look at what we have. We've got a sine squared, we've got a 2 sine theta, we've got a minus cosine squared theta plus 1. These two have sines. This one has a cosine squared. To make it easier to work with, what you're probably going to want to do at this stage is make all of these terms in the numerator be all sines or all cosines. And since I can't really convert just a plain sine theta into a cosine, but I can turn a cosine squared into a sine squared, that's what I'm going to choose to do using that Pythagorean identity. So sine squared plus cosine squared equals 1. Therefore, cosine squared is 1 minus sine squared theta. So I'm going to substitute that in right here in parentheses. So this numerator becomes sine squared plus 2 sine theta minus parentheses 1 minus sine squared theta plus 1. If I distribute my negative, I'll get a minus 1 and a plus sine squared theta. The 1's cancel out, and sine squared plus sine squared becomes 2 sine squared theta plus 2 sine theta all over 2 sine theta cosine theta. Hopefully you're starting to see the light here a little bit, because that numerator has a 2 and a sine theta that I can pull out like a GCF. So we are making progress. If I factor out that 2 sine theta, I'm left with a sine theta plus a 1. And finally, that 2 sine theta on top will cancel with the 2 sine theta on bottom, giving me sine theta plus 1 over cosine theta, and that is what we were trying to prove. So we got it. So it had to get messy before it got simpler. And the other really tricky part was knowing to multiply by that conjugate. And that just takes some experience. And usually I try that whenever I have fractions like this, where there doesn't seem to be any other first step. I couldn't use any identities right off the bat. There weren't any fractions that I had that I could get common denominators for. I was pretty much stuck right from the beginning. So that's when I pulled out of my pocket this idea of multiplying by a conjugate. All right, next example. Secant theta over 1 plus secant theta equals 1 minus cosine theta over sine squared theta. So which side should we start with? It really doesn't matter, but in my preference, in my experience, when I look at that left side, I see those secants, and I know that in my goal over here, I want to turn them into some cosines and some sines if I can. And at least I know how to turn secants into cosines using that reciprocal identity. So that gives me a place to start. So by looking at this equation, that left side, it gives me more opportunities to work with. So the very first thing I'm going to do is change these secants into 1 over cosines using that reciprocal identity. Now what that does is it creates what we call a complex fraction. Fractions within fractions, which may look bad, but it's actually good because it gives us something to do next. It gives us the next step. In order to clean this up, what we can do is multiply by a fancy version of 1 again. But this time we're not going to use the conjugate. This time we're just going to use a common denominator. If I look at all these denominators, cosine theta is my common denominator. So I'm going to multiply by that on the top and on the bottom. Now when I multiply 1 over cosine theta times cosine theta, those cancel out, just giving me 1. On the bottom, 1 times cosine theta stays cosine theta, and 1 over cosine theta times cosine theta, those cancel out as well. So I get cosine theta plus a 1. So now this looks pretty clean, but it's not what I wanted it to be over here. And I can't convert cosine theta into anything because it's not a square, so I can't use those Pythagorean identities. There's no common denominator anymore that I have to worry about, so I'm kind of stuck. Doesn't look like I have anything to do here at this point. So that's when you pull out that that conjugate trick again. If you have a fraction and you're stuck because it looks pretty much simplified, then try using the conjugate. So I am going to use the conjugate of the denominator this time because that's the only stuff I have to work with. So the conjugate would be cosine theta minus 1, and I'm going to multiply by that on the top and the bottom so that I keep my fancy version of 1. So the top just becomes that conjugate, cosine theta minus 1. On the bottom, remember there's implied parentheses here, you would need to FOIL this out. So let's go ahead and FOIL. Cosine times cosine is cosine squared. In the middle, we'll get a plus cosine and a minus cosine, so those will cancel out. And then plus 1 times minus 1 is just minus 1. Okay, it still doesn't quite look like what we wanted up here, but it now has a cosine squared involved, which means I do have that Pythagorean identity, cosine squared plus sine squared is equal to 1. And remember, we have a cosine squared in the bottom right now, but we want to turn it into a sine squared. So what we want to be doing here is replacing this cosine squared with something in terms of sine squared. So let's solve this for cosine squared by subtracting, and I'm going to substitute all of this right here. So this becomes cosine theta minus 1 over 1 minus sine squared theta minus 1. Notice the 1's cancel, and we have cosine theta minus 1 over negative sine squared theta. And that's almost what I want, but my signs are backwards. So all I'm going to do is factor out a negative from the numerator, which makes this negative cosine theta plus 1. And then I'm going to cancel out the negatives on the top and the bottom. And finally, to make it look exactly like that right-hand side, addition is commutative, so I'm going to switch the order around here. and make this a subtraction instead of a sum, and now it looks exactly like what I wanted on that right hand side. So we got it. Okay, so this one had lots of tricks. First we used that reciprocal identity to make some fractions, then we multiplied by the common denominator to simplify the complex fraction. Then we had a conjugate to use because we were kind of stuck. Then we used Pythagorean identity to get rid of that cosine squared, and then we just did a little bit of factoring at the end. Okay, next one here, number 7. So we've got 1 minus sine theta over 1 plus sine theta, and we want that to equal secant theta minus tangent theta quantity squared. So which side should we start with? Again, it doesn't matter, but to me, there looks like there's more potential to do some work if I use this right-hand side instead of that left side, which looks fairly simplified to me. So I am going to work with the right-hand side this time. Now you have lots of options here in how you want to approach this. To me, my first instinct is to go ahead and square this quantity out so that I can get some of those secant squareds and tangent squareds, and then kind of pull out of my pocket those Pythagorean identities that involve secant squareds and tangent squareds. So that's kind of my game plan. So this is a whole quantity squared. So if we square this out, we're going to get a secant squared theta. You are going to get a middle term. You'll get two of them, a minus 2 secant theta tangent theta, and then you'll get a plus tangent squared theta. So that's just from FOIL. Now at this point, what I would want to do is try and use some of those identities if I can. And you have some choices here. We know that tangent squared x plus 1 equals secant squared x. So do we want to replace the secant squared and turn it into tangents, or do we want to turn this tangent into secants? It's kind of up to you. So just take your pick here. I'm going to do it on the end here. So I'm just going to take this tangent squared and I'm going to change it into a secant squared minus 1. Now just because I'm doing it this way doesn't mean this is the only way to get your answer. There are other ways to solve this. So I'm going to change this tangent squared to a secant squared minus 1. Okay, so this is just my way of doing it. It doesn't mean it's the only way. And sometimes I don't always pick the most efficient way, so if you do it a different way and you get that answer quicker, great. That's not a problem. Now that I have this secant squared theta in there, now I've got two of them. So let's go ahead and combine those. So I have a 2 secant squared theta. A lot of this is just kind of following your nose. You may not know exactly where you're headed. Like at this point, I don't quite know how this problem is going to turn out, but I'm just going to keep trying things and hoping that it's making progress towards that left side. So when I get to this point, I still have some secants and tangents in there, and I'm kind of stuck. I could go back and maybe try to turn this back into a tangent squared, but then I'm going in circles and I'm going back to that starting point. So at this point, I've cleaned it up as much as I can. I've gotten rid of that big square. I've used that identity as much as I think I can do. So this point, what I would probably recommend is trying to get rid of these secants and tangents altogether by converting everything in terms of sines and cosines, especially since on the left-hand side here, all I see are sines. So at this point, what I would probably do is change this secant squared into a 1 over cosine squared theta, and then change this secant into a 1 over cosine theta, and change this tangent into sine theta over cosine theta. So getting rid of all of those secants and tans right away. And you could have done that from the start up here too. Okay? There's many, many ways to do this problem. So let's just clean this up a little bit. This becomes 2 over cosine squared theta. And doing all these tops multiplied together gives me 2 sine theta over all these bottoms, which is cosine squared theta, and then minus 1. Now this is pretty good, except I have 2 common denominators here, but this 1 does not have a common denominator. So you might want to change this 1, instead of writing a 1 there, let's change it into something equivalent to 1 that has a denominator of cosine squared theta, so it would have to be cosine squared over cosine squared. So there's my 1, but I've done it so that now I can consolidate all these fractions since they all have the same denominator. So we get a 2, a minus 2 sine theta, and a minus cosine squared theta. Okay, are we making progress? Well, we've got a sine in there. We want all of these to be sines. So the next thing I would probably do is change this guy and this guy into sines using that Pythagorean identity. So if cosine squared plus sine squared is 1, that means cosine squared is 1 minus sine squared. So I'm going to substitute that in right here using parentheses because you do have a negative in front of that cosine squared, and I'm also going to substitute it into the bottom. So that way I'm trying to convert everything in terms of sines, and now I don't have any cosines left. If we distribute on the top, we get a minus 1 plus sine squared theta. Let's go ahead and put this in descending order. I'm going to put that sine squared first, then I'm going to put that minus 2 sine theta term next, and 2 minus 1 is positive 1. At this point you want to think factoring. Factoring is huge in these identities, so usually there's going to be a point where you probably are going to need to factor. So next here, this numerator will factor because it's like a trinomial. If we have a sine theta times a sine theta, we'll get that sine squared. If we have a 1 and a 1, we'll get this 1, and I need them both to be minus, so my middle term is a minus 2 sine theta. The denominator also factors because it's a difference of squares. So a 1 and a 1, a sine theta and a sine theta, one of these has to be plus, one of these has to be minus. And then finally, what you're looking and hoping for is that you have some factors that will cancel. Unfortunately, my order is a little bit backwards on the bottom, but these two things will cancel, but they're really opposites. They're not actually equal to each other. They're opposite in signs. So they cancel, but they cancel to a negative 1. So this is going to give me a negative times this leftover factor in the numerator over this leftover factor in the denominator. And if you distribute that negative across, and then you switch your order around because addition is commutative, this becomes 1 minus sine theta all over 1 plus sine theta, and that is exactly what we were trying to get way over here. So we finally did get it. Okay? Alright, next example. Here's what we've got. We've got a lot of stuff to work with on the right and not a whole lot to work with on the left. So I'm going to work with the stuff on the right. And I am going to go ahead and sort of do what we did in the last problem. And I'm just going to go ahead and replace all these secants and tangents with sines and cosines because that's all I see over here on the left side. So let's just jump right in and change this secant squared beta into 1 over cosine squared beta. And then tangent is sine of beta over cosine beta, and secant beta is 1 over cosine beta. So when I multiply those two fractions together, I get sine beta over cosine squared beta. And that's good news because I now have a common denominator. And on the top, I just get 1 plus sine beta. This is very, very similar to the last example. At this point, what we're going to do, since I only have sines in my left side, let's go ahead and change this cosine squared into a 1 minus sine squared beta. And as I said, this is very, very similar to the last problem. At this point, if you remember what we did in that last example, this denominator will factor into a difference of squares. 1 minus sine beta and 1 plus sine beta, which is good because that 1 plus sine beta factor cancels out, giving me 1 on top and that 1 minus sine beta on the bottom. So we got what we wanted and we finished. Okay, next example here, tan squared minus cotangent squared equals secant squared minus cosecant squared. So which side do you want to work with? They're probably equally as difficult to work with. They equally have as much potential, so it's totally up to you. I'm just going to go ahead and work on this right-hand side. And when I see those secant squareds and those cosecant squareds, I think Pythagorean identities. So let's remember that tan squared plus 1 equals secant squared, and 1 plus cotangent squared equals cosecant squared. Those are our Pythagorean identities. Now this is good news because we're trying to take secant squared and we're trying to turn it into a tangent squared. So I'm going to substitute in for this secant squared what it's equal to, which is tan squared x plus 1. And then I'm trying to replace this cosecant squared with something in terms of cotangent. So I'm going to replace this cosecant squared with what it's equal to, and I'm going to use parentheses because there is that negative in front. So this becomes 1 plus cotangent squared x. So we're getting those tangents and those cotangents in there that we want from that left side. Let's go ahead and get rid of our parentheses by distributing where necessary. So this becomes a minus 1 minus a cotangent squared x. The 1's cancel, and we're left with tan squared x minus cotangent squared x, which is exactly what we wanted, so we got it. Okay, next example, number 10 here. Sine cubed x plus cosine cubed x over sine x plus cosine x equals 1 minus sine x cosine x. So which side should we work with? Well, on the right side, there doesn't seem to be a whole lot that we can do. We don't have any squares, so we can't use any Pythagorean identities. It's already in terms of sines and cosines. There's no fractions that we can manipulate, so we're pretty much stuck on that right side. On the left side, you're going to be stuck as well unless you remember that that numerator, sine cubed plus cosine cubed, is a sum of two cubes. Therefore, it will factor. And if you don't remember how to factor these, then you're going to be kind of in trouble here. You're not going to have much to go on. But this does factor. What it factors into is two sets of parentheses. The second set of parentheses is actually going to have 3 terms in it. The first set of parentheses has only 2 terms, and these 2 terms are just the cube roots of each of these 2 terms. So this has to be just a sine x plus a cosine x. You use the same sign that you had up here in the original problem. Once you know these 2 terms, then this second factor is the sine x squared. That's the first. On the end is this cosine squared, and in the middle it's these 2 multiplied together, so sine x cosine x, but with the opposite sign of what you have here. So if this is plus, this middle term has to be a minus, and the cosine squared term is going to have to always be a plus as well. Now if you were to FOIL this out, you would notice that all those middle terms will cancel out, and all you would be left with is the sine x times the sine squared, which is your sine cubed, and your cosine x times your cosine squared, which is your cosine cubed. Everything else cancels out. So that's why it works. But it's hard to know this without having memorized that factoring formula for a sum or difference of cubes. So how does this help me? Well, the first good news is this factor is exactly the same as the denominator. So those cancel right out, leaving you just sine squared x minus sine x cosine x plus cosine squared x. The other good news, hopefully you realize, is that these two, they're plus, so sine squared plus cosine squared is 1. So we can replace sine squared plus cosine squared with a 1, and then this middle term is still left over. And that is exactly what we were trying to prove, so we got it. Okay, the next example is a little bit different, but it is something you will see again in calculus, especially in Calc 2 when we do integration. This is something that we often do in calculus to help make the problem become something we can work with a little bit easier. It's called a trig substitution. So what we have is this expression 1 over the square root of 4 plus x squared. And all I'm asking you to do is to substitute in for x the expression 2 tangent theta and kind of see what happens. So I'm going to take this x and I'm going to replace it with a 2 tangent theta, and that x was being squared. So what happens if we square that whole quantity? We're going to square the 2 and we're going to square the tangent. So we get 4 tangent squared theta. Now notice that both these two terms in the bottom have a 4. So I'm going to factor out a 4, and that leaves me with a 1 plus tangent squared theta. Now hopefully that's ringing some bells for you, because we've done this several times today. Tangent squared plus 1, or 1 plus tangent squared, is secant squared. So we can replace all of this with a secant squared theta. So this becomes 1 over square root of 4 secant squared theta. And that's good because that's a perfect square, so is the 4, so we can simplify this into a 1 over 2 secant theta. And finally, if secant theta is in the bottom, what does that turn into? Remember, secant theta is the reciprocal of cosine. It's a 1 over a cosine. So 1 over a 1 over cosine theta just becomes a cosine theta. So this secant theta in the denominator is going to flip up to a cosine theta in the numerator. And that 2 is still in the bottom. So you can write your answer like this, cosine theta over 2, or sometimes we would just write it as a 1/2 pulled out front, and then that cosine theta on the side. So we took this expression and we were able to turn it into just 1/2 cosine theta. Okay? Last example. We've been proving a lot of identities today. Now what I want to do is show you how to prove something is not an identity. And this is hopefully a lot easier to do, because all you need to do to show that something is not an identity is basically find a counterexample. Find, in this case, an x and a y that if you were to plug them in would not make the equation true. Because if something is an identity, then it should work for every x and every y. So if you can find one x and one y where it doesn't work, then it can't possibly be an identity. So we're going to find a counterexample. And you can get creative here, but you don't need to. Just try to pick something relatively simple here. So I am going to just pick x is equal to and y is equal to, let's just pick some nice angles that we know. Let's just do pi over 4. Okay? You could try zeros, you could try pi's, you could try pi over 2's. It's totally up to you. Some of those may occasionally work, but you just kind of play around with choices for x's and y's until you find one where this doesn't work. So let me show you what I mean. If we plug in pi over 4 for x and pi over 4 for y, we're trying to show that what we get on the left side is not going to be the same thing that we get on the right side. So what's pi over 4 plus pi over 4? Well, that's 2 pi over 4, which simplifies to pi over 2. And what's the sine of pi over 2? Well, that's the sine of 90 degrees, and the y coordinate at 90 degrees is 1. So sine of pi over 2 is 1. What do we get on the right side? Well, sine of pi over 4, remember your pi over 4 angles have a terminal point of root 2 over 2 for x and root 2 over 2 for y. So both of these are going to be root 2 over 2's. And if I have 2 of them, then that makes 2 root 2 over 2's, and the 2's cancel, so this is just root 2. So on the right side we get root 2, on the left side we get 1, so we just found a counterexample that proves that this is not always true. Okay? So proving trig identities, it's a very tricky topic, and the best advice I can give you is practice, practice, practice. Be prepared to be a little frustrated at the beginning. You really want to have memorized all of those identities, and when you're first starting your homework, it's a good idea to have that memorization sheet, the one that we had earlier in the notes, have that handy next to you so you can refer to it. And remember to look for fractions, get common denominators, try factoring, try multiplying by a conjugate if you get stuck, try converting to sines and cosines, and using all of those identities to help transform one side of your equation into the other side. Good luck! That concludes our lecture on proving trig identities.